Hello, next is the idea of work. So when I talk about work, when any physicist talks about work, they're not talking about what you call work in either the a job sense or in the sense of, oh, that was a lot of hard work, you know, lifting stones and moving stuff. So when we talk about work in the physics sense, you got to keep in mind that it is not the same work as what you are used to. Okay, and we'll get Bodhi in here. Hello, Boudica. This is my brave and bold body chair. Yeah, okay. Down you go. You've had your little time in the spotlight. So when we talk about work, it's got something to do certainly with, if you think about what is a lot of work. Well, I just said carrying stones. Yeah, okay, carrying something, lifting something. Work has to do with something being moved over a distance. So it's got to do with distance, something being moved or moving itself. And it also has to do with how much force is being applied. So if I have, for instance, a, 25-pound barbell, then you know that lifting up, down, this is really bad for my hands, lifting up, down is a lot of work. But I'm going to argue right now that carrying this and just walking sideways, so just walking like this, carrying it like that, that's not any work in the physics sense. And so you say, well, that is just a load of crap, because I know that it's work. If you're carrying something really heavy, even if you're moving across a flat parking lot or something, you know it's a lot of work to carry something that's really heavy. But I'm going to argue that, nope, it isn't. Because our definition of work in a physics sense is the parallel force times the distance. Is actually a cross product if you do your calculus version. But for now, we're just going to talk about it as a multiplication. It's the parallel force times the distance. Well, okay, a bigger distance means more work. That makes sense. Parallel force. What the heck is that? The parallel force is the amount of force that's being applied in the direction that the distance is. So when I'm carrying something, so I have something in my hand, well, the force I'm applying to it, the force of me on the object, is upward. We've got the force of gravity pulling downward. And if I'm just holding it there, no work. There's no distance. You know that if I lift it up, that it's hard. It is work. And I just said that if the distance is this way, then the work is 0. That's what it means by parallel. You have to have a force that is in the same direction as the distance in order for it to be work in the physics sense. And those are perpendicular. The force is this way, distance is this way, no work. So why, if I tried to carry that 25-pound barbell, even across a flat surface, it would be work. Why would that be? So you know it is. It isn't as much work as lifting something straight up. Well, that's because if you think about when you walk, I'm going to exaggerate this, walking, you're actually going up and down each time. So when you're carrying something, it is moving up and down a little bit every time. Every time you lift it up, force, distance, parallel, it's work. So yes, it is actually a little bit of work to carry something. If you could slide it without it moving up or down at all, no work. I could put that thing on a rolling chair and move it parallel to the ground, and I wouldn't be doing any work on that because the force would be this way and the direction, this way and then that way, perpendicular. Okay, so parallel is key. Now we just got done with the torques unit. And with torques, you remember we had torque is the perpendicular force times the lever arm. This is the complement to that. I don't know what to call it. It's the other part of that. Perpendicular force causes rotation. Parallel force causes work. And so that's one thing to keep in mind. Torques, we're out of the torques. We're not going to deal with rotations anymore, so we don't have to worry about that. All we want is the parallel force now. And so when I'm doing problems, I often draw a little arrow off to the side showing the direction of motion, because then it's easier for me to see what in the problem is actually going to be doing work. So let's do an example. What should we do? What shall we do? Okay, let's suppose you are pushing a heavy crate across the floor, and you're pushing down on it. So if we do the force diagram for the crate, what forces are acting on the crate? Well, the earth is pulling down, the floor is pushing upward, supporting it. There's going to be some friction opposing the motion. And I said I'm pushing down on it, so there's my pushing force. And that is all we've got. Now I'm going to do that little arrow saying the direction of motion is this way. So there are 4 forces here. Which of them are going to do work? Which of these 4 forces do work? The only things that do work are things that have a component, hint, hint, a component in the parallel direction. So what I will often do, shoot, I don't have a meter stick. What I'll often do is I'll take a ruler and I'll line it up with my direction of motion. I'll just do it with a marker. So my direction of motion is like this. So which of these forces line up with this? Well, that one clearly does. Perpendicular? No. Perpendicular? No. What do we do about this? Well, okay, gotta go back to the components. There is a parallel component and there is a perpendicular component. This does have a parallel component, so the pushing force does do work. You do work pushing on the crate. Friction also does work. Now, do you think that these are going to be the same sign of work? Are they both going to be adding energy to the system, positive work? Are they both going to be taking energy away, negative work? Is it going to be one of each? Well, if we think it through, if you think through what friction does friction reduce something's energy or does it give something energy? Well, most of the time, in this case, it's reducing the energy. So I would say, in this case, we have negative work done by the friction force. It's taking away energy from the system. And the pushing force, is that adding energy to the system or taking it away? Well, I'm pushing on it and I'm making it move, so I would say that I'm adding energy to the system. So positive work done by the pushing force. Now you can think your way through that for every problem. Say, do I think this is adding energy? Do I think this is taking away? Or you can just use this rule of thumb. It's positive work if F, I just said friction, oops. It's positive work if the force and the distance are in the same direction. So they're both like that. And it is negative work, you can probably guess what's coming. Negative work is when the force and the distance are in opposite directions. So that's what we've got here. Direction of motion is this way to the right, friction is to the left, negative work. The pushing force, the component of the pushing force that is parallel is going to the right, direction of motion is to the right, positive work. And so the equation we're going to be using is the parallel force times the distance traveled. And in terms of the sign, you can think your way through it every time, or you can just keep in mind, okay, it's positive work if the force and the distance, if these two are in the same direction. It's negative work if the force and the distance are in opposite directions, like that. So there is an example of work and how you determine if there is work in a problem, and what you would do if you have like lots of forces and you have to say, oh, okay, what does work? 4 forces, turns out there's only 2 work terms. So that is the basics of work. The only other thing I want to note about work is this little sneaky guy right here. If we just have something going, whoop, and you're lifting something up, so let's say you've got something in your hand and you're just lifting it straight up, okay? So direction of motion is like that. And what forces act on, let's say it's just a marker in your hand. Well, we've got the weight, and we've got the force of your hand, and that's it. So you might say that, okay, they're parallel and same direction, positive work. This is parallel and opposite direction, negative work. Unfortunately, we have already taken into account the effects of gravity. So where would we do that? Where have we taken into account the effects of gravity? Well, we take that into account with this term, the potential energy due to gravity. So that takes into account the fact that, oh, gravity is doing something, or we're doing something against gravity. So do not double count. Do not double count the work done by gravity. So you should, let me write this big. I'm going to write this big so that it's very clear. You should never have a work done by gravity term. I can talk. So you should never. There's never going to be a work done by gravity, because we already took that into account with the potential energy due to gravity. So never going to have that. So if you have that in your equation, you say, oh shoot, I'm double counting it. And your math will be all wrong because that is effectively the same as that. So that's the only thing I wanted to remind you about with work. So direction is important. Direction is extremely important. Yep, you only want the parallel forces, the forces that are parallel to the direction of motion, and then depending upon if they're the same direction, we have positive work. If they're opposite direction, we have negative work. And then don't ever have this term because we took into account gravity right there. All right, good job.